So yeah, I wanted to start us off with some updates to tell you what the Google AI Quantum Lab has been up to since the last year's symposium. And I have the privilege to talk about the achievements and results of our team. But of course, I want to acknowledge the fact that we have a hardworking and very talented team. So it's hard to give credit at every place where it's due. So here you see the list of people we are working with. And our team is steadily growing. And we are always eager to increase our intellectual horsepower and our intellectual diversity. So if you like our work and you think you would like to contribute, I have something to contribute, don't be shy, contact us. So I have a few messages that I wanted to share. So the first is we are opening. And when I wrote down this line, I didn't expect it would have such a fraught meaning, but it's rather innocent what I mean here in our case. Many people on the video call, I'm sure, have visited our laboratories in Santa Barbara and been to this place we call lovingly GQ1, stands for Google Quantum One Laboratories. But they're now being joined by a much larger facility called GQ2. And you may have seen this architectural drawing a few times. We showed this before. But what's exciting to us, as you can see in this picture, which was just taken a few days ago, the facility is almost ready to go. Actually, if it wouldn't have been for COVID-19, we would be in there right now. Actually, a number of our dilution refrigerators preceded us. They're already installed, and we are taking already data out of this facility in a remote fashion. So if you wanted to use Google's upcoming quantum computing service, you would do this in the following way. You would be placed somewhere, let's say your favorite quarantine hangout, then you download Circ from GitHub. That's a development environment where you would formulate your quantum algorithm. Then you send it to our service. Our service name is Quantum Engine. And then you have a choice. Probably initially you would just go to simulators. Those can be used then to double check whether there are any bugs, or at least in a noise-free environment, your code works. And then you transfer it over to the actual quantum processors. So we have an increasing fleet of quantum processors available in production. There are older processors that just have 20 qubits, but our fabrication team, led by Tony Migrant, they have actually braved COVID conditions and started to fabricate 72 qubit processors, and they hopefully will join the fleet in production soon. You also have, or for additional scalability, we have added machines in Google Cloud. Those are high memory machines where you can do simulations up to 38 qubits. 38 qubits a little bit the sweet spot. If you go beyond this, it gets expensive on our side. We have to add quite a bit of machines. But in my experience, I have yet to see a simulation in the 40th qubits where we would see a phenomenon we haven't seen at 38. So it's a good testing ground. Then there is a software stack. I'm sure many on the call are already familiar with it. So beyond Quantum Engine and the Circ programming environment, you find things such as OpenFermion. It's a library for quantum simulations, particularly quantum chemistry and electronic structure calculations. If you happen to be interested in quantum machine learning, a burgeoning field, then you may like TensorFlow Quantum as a library to work with. And then there are various other environments. Eventually, there will be vertical libraries that would support activities or tasks such as certifiable random number generation. So this afternoon or a little later this morning, you will hear a talk from the two leads of this effort from the hardware side, Eric Lucero, and then Dave Bacon from the software side. So the next message is that we have need toys, or let's be more corporate about it, we have need tools. And they're various, but what I wanted to show is a tool I think is piece of art, and actually it was done by our physics team led by Vadim Smilyansky in collaboration with Yu Chen's metrology team. And what this tool does, anybody who has ever run quantum algorithm on a processor knows that you have to tune it up, you have to calibrate your processor well before you start. And for example, you have a gate operation. Let's say you have a swap gate, and it's characterized by an angle theta. And now you need to know or put this theta exactly at a known value. So with this new tool, we can estimate the parameters, the coherent parameters in our circuit, better than 3 times 10 to the minus 5. Moreover, as you can see in this figure, we understand the theory very well. So there is theory and experimental results for this tool line up really well. And it's not only high precision, state-of-the-art precision, it's also very fast. So you can actually outrun calibration drift, which is also quite important. So you can see that you stay below rather low error levels during duration of extended computations if you invoke it in between. It is also very scalable, so you can simultaneously tune up all the parameters in your circuit and be sure that you get, or be sure, have a good probability that you get at the end high fidelity results. So the next message is that we may be on the verge, we may be able to implement commercially or scientifically interesting NISC applications at this point. And I should say internally we have the notion of a gold standard for a NISC publication. So this gold standard essentially would consist of the following features. Obviously, you want to compute something of commercial or scientific interest. But second, ideally, you want to have this computation be beyond the reach of classical machines. And third, we would like to require that the circ code is open sourced. This will lead to a growing library of good examples that other researchers, fellow researchers can build on. Now, even though we dub this a gold standard, that doesn't mean there isn't any other good works that can be done in the NISC era. Of course, important proof of concept stepping stones towards the gold standard can be excellent work. Or if you have ideas for error mitigation and want to try those out, these are all pieces of work we support as well. And I say we support as well because, as you will hear throughout the conference, there are various funding vehicles we offer for those who want to or have a suggestion for an algorithm and want to run it on our machines. So here I give you a little laundry list of the different algorithms we have already run. And actually the service launch, even though I showed you the picture of GQ2 where it stands right now, it's important to know that this service has already been launching for a while, since last year. And at Google, we have these cutesy names. We go through a fish food phase, a dog food phase, and cat food. And then eventually in German, we would say Schluss mit lustig, the fun ends, and we become all corporate and call it now the early access program, as the door opens to the external world. So fish food, this was a phase defined by just people from our own team, the Quantum AI team, were running algorithms. So of course they have insider knowledge, they know about all the bugs and the quirks of the hardware. And they were able to run algorithms such as the quantum approximate optimization algorithm. They prepared Hartree-Fock states or did interesting pings looking at out-of-time order correlations. Actually, the talk right after me will give you the details of these experiments. And then in the next phase, we widen the circle. We go to alphabet as a whole and invited our colleagues who now have less knowledge about the intrinsics of our offering. Hey, please, if you feel, run some algorithms. And we got interesting work, for example, from X. You will hear about this later today, where they simulate quantum gravity situations on an actual chip. And some other work I'm rather excited about that we may be able to run at some point is to compute NMR spectra for molecules, think of proteins bound to surfaces or proteins bound to membranes. And then the final phase that's opening soon and will run through fall is we invited, and many of you participated, the wider community to submit proposals, and we selected the cream of the crop, and we have nice suggestions by companies such as Phasecraft to do a quantum simulation of the 2D Hubbard model. Michael Lukin from Harvard, Manuel Enders suggested to study phenomena near quantum critical points. So there's a nice list of experiments we are looking forward to running. And also about some of them you will hear actually in the talk tomorrow. Tomorrow will be when we hear from, not from Google, that's today. Tomorrow we will hear from our collaborators. Then the area that I'm do hands-on working myself, quantum machine learning, wanted to quickly give you an update there. There's sort of a set of beliefs or convictions that's shaping up. It needs more work and it's definitely not proven, but the following things or statements seem to be true. That we can do basic machine learning operations, such as preparing probability distributions that describe data distributions, or we can do feature maps into a high-dimensional Hilbert space that are expensive to produce on classical machines. Or I should maybe say that possibly even beyond the reach of classical machines. And then if we use those machine learning primitives, then when we apply them to data sets that are manifestly quantum in the sense that they're classical data sets, but they resulted from measuring an entangled quantum system, then we seem to have advantages, let's say, in terms of sample complexity. What is less clear is, would these primitives also help us when we go to a general machine learning data set? And even though I have to say we got some beginner's luck here, for example, we ran a quantum GAN, a quantum generative adversarial network for the plain vanilla MNIST character data set, digit data set. And we found that indeed we could produce with small Fredget distance, this is sort of a metric, getting good quality images synthesized. But we still need some more. This might have had nothing to do with quantum resources per se. We might just have been lucky and stumbled on an architecture that worked well. So there's definitely some more ingenuity needed here, but it's ripe for doing something interesting. And on that note, I wanted to explain the following. When we try to discover diamonds, as Baba called it, interesting quantum algorithms, and we do it with our scarce resources. We have only that many people, we only have that many processors. Then we followed the principle at Google that has served Google well, and that says, develop for the pro first. So if the nerd in the family loves your software product, then she will explain it to her siblings, she will explain it to her parents, and this is typically a good way to spread software. And we have done the same thing with with quantum computing, where we reached out to top institutions, top researchers first, and definitely this yields results. But there are two events that recently happened that have made me question whether this should be our sole approach, or we should start earlier than we had planned to complement this by a more broad outreach approach. And the two events were, I was working with my intern, Alex, and one day he blurted out, oh man, it is so hard to think about interference patterns on a hypercube. We need to start, third graders to think about this. And there's some truth to it. None of us are really trained well in the art of crafting a quantum algorithm, which, as we know, is really the art of crafting an interesting interference pattern. And sort of bringing in a fresh, unspoiled minds, there's something to be said for that. And the second event that happened, as we are all aware, sort of discussions around diversity and inclusion have heated up over the last months tremendously. And diversity and inclusion is all about breaking down barriers to opportunity. So with the new cloud-based simulators, we can essentially provide Google scale, worldwide scale of access to quantum computing resources, at least to the simulators. And there is an opportunity to enable or find the Ramanujan of quantum computing. Many of you will know Ramanujan was born in the 19th century in rather modest circumstances, taught himself math, but came up with these amazing formulas that amazed the contemporary top mathematicians of his time. So if you are a kid in a town in India or a kid in a village in Kenya, as long as you have a good enough internet bandwidth to watch low bandwidth YouTube videos, you have enough internet connectivity to participate in our quantum service. So this seems to be a nice win-win. So one more thing. We spend a lot of time since we reached beyond classical computation results to now think ahead. And we worked hard with actually a large part of the team on a plan to build an error-corrected quantum computer. So this work was shepherded by our quantum hardware team, and with the leads I should acknowledge here are Julian Kelly, Anthony Migrant, and Yu Chen. Of course, there's much broader and larger teams underneath them, but they have worked on, jointly with the theorists, on a roadmap that looks 10 years out. But we think, to allude to this famous Kennedy quote, we think we can do it before the decade ends. What way can we do? We think by then we can build a large error-corrected quantum computer with 10 to the 6 million physical qubits. And in essence, this would be an information architecture based on the surface code supported by transmon qubits. And we developed a tight schedule of well-defined, there's actually a telephone book thick of calculations and designs behind this. So we have a tight sequence of difficult, but we feel reachable milestones that eventually take us to this end goal. So let me talk to you about our next big milestone, which is the demonstration of a logical qubit. So, or I should rather say the demonstration of reduced logical error. We all know that error correction at the end of the day works by introducing redundancy. So you have to take the information encoded in your logical qubit and distribute it over a set of physical qubits. For example, a 2D array of, let's say, 3 by 3 data qubits that would hold the quantum information. Or you can go to larger sets, 5 by 5, 7 by 7 arrays. And those data qubits do hold the information. Then, of course, you have to peek in a quantum circumspect way as to not collapse the logical state. So you would do this by introducing measure qubits, which essentially do parity checks. And based on the parity measurements, you can get a sense of, did anything go wrong in my circuit, and then correct it. So what we can also do to complement this, ultimately we know we have to correct against 2 errors, phase flip and bit flip errors. But to buttress this work, we can also study one-dimensional codes by snaking in sort of a 1D architecture into the 2D array, and study repetition code or phase flip code as well. The advantage is you can go out to higher code distance. So what we are aiming for is eventually we want to publish a paper that will have a figure a little bit like this. And this is sort of cartoon figures, not actual data yet, but just to show where we are going towards. So we want to show that as you increase your code distance, the logical error rate comes down. And you want to have a nice suppression factor, meaning as you go from 3 by 3 to 5 by 5, you want to see, let's say, a factor 10 reduction of your logical error rate. So this is what we would like to demonstrate next. And to see how far away we are from this, we did some theory, a model. Actually, my dad always used to say the most practical thing there is a good theory. And we developed a component model, which essentially after every operation that you use in the surface code, you introduce a simple Pauli error channel. And then armed with this error model and putting in the actual numbers, you have sort of a tool to chart the road into the future. For example, we would see that if today, so here's these different bars tell you, so how bad is our CZ error, or how bad is our Hadamard error? Oh, sorry, it's the other way around. It's a small one here, see Hadamard error, CZ error. Actually, something we found and that surprised us and was not properly accounted for in the literature so far is idling errors matter a lot. And of course, in hindsight, not surprising, if your qubit is sitting there and you suffer from T1 processes, then obviously your overall error accumulates. So if you apply this simple error model and we would run it today, actually our lambda or suppression factor would be smaller than 1. That means actually our error would increase as we go to larger arrays. But it also gives us an idea how we can reduce the different error budgets and then make the proof of principle work. And then eventually our roadmap target is to get the overall suppression factor to about 10. And we definitely do think this is feasible based on calculations we made. And based on what I said about the idling error, there seem to be two basic roads forward. One is you reduce your idling error, or you reduce your cycling time, which is cycle time, which is of course good in its own right. You have a faster computer this way. So you focus on circuit design to make things better. And for our team, this is a little bit in our DNA as imprinted on us by John Martinez. But you can also do a complementary approach. They both can live next to each other, where you focus more on materials research. So let's say the Yale School of Thinking would look more into this direction. So here you would aim at longer coherence times, let's say in the hundreds of microseconds, where if you make your cycle time faster, you may get away with tens of microseconds. And of course, you can do both pathways. So unfortunately, the simple error model is not quite enough. There are extra or additional error channels. There's leakage, there's calibration drift, there's crosstalk, there are correlated errors. And we understand that correlated errors have always been sort of the boogeyman of quantum error correction. There are not good threshold theorems known today. Actually, our physics team started to work on exactly those. And correlated errors are not sort of a theoretical thing. They easily occur when, for example, a leakage state decays into states that are valid in your code space. Or a much more dramatic example of correlated errors is the impact of cosmic rays on our qubit arrays. And we do see this. Actually, this is a trace here, 25 microsecond duration, where we actually just run repetition code experiments, and we do see those bursts of errors happening that happen in a spatially and temporally correlated manner. So if now you think, oh my God, we will have to take quantum computers down to a mine shaft. No, it's not quite that bad. We just will have to install phonon traps, but this is something you will have to take care of. So this was a 10 to the 2 milestone. Then, of course, you would just make your code distance large enough that you approach about 1,000 physical qubits at that time. If everything goes well and you have a large suppression factor, you should have coherence times of years, or what I like to say, essentially your device should stay coherent until you switch off your computer. And then there is a milestone that I should maybe point out. It's important from an investment and financing perspective. Eventually, you will have 2 logical qubits at hand, and you have a full gate set between them, and hopefully not just Clifford gates, but a complete gate set. And at that point, you really have what may be called the integrated circuit of quantum computing. You have a tileable digital module. And to build a large machine, you would just take this module and replicate it. And this is maybe not too far out, 5, 6 years, somewhere there, hopefully. And it's important because past that point, the risk profile for quantum computing comes way down. It becomes more the risk profile of building a high-rise or freeway rather than doing cutting-edge quantum electronics. And now, fast forward to the final milestone. Here I want to give you picture how we envision a 1 million qubit error-corrected quantum computer to look like. So it will consist of these modules that we tile. And as I say, there is like quite a thick book of technical information that went into this design. And something you see here, the scale is about right with the figure, a human figure placed there. So there's sometimes this misconception, oh, superconducting qubits, they require these thick wires and you will eventually need a factory floor full of dilution refrigerators, will be used, expensive and unwieldy. This is actually not true. If you spend a careful time designing and thinking about your control electronics, about wiring solutions, then you see you would be able to deliver a product in a manageable size. So with this, I want to summarize a little bit and also issue a call to the community to help us in various aspects. So we feel we have a good plan, a plan of record that says a 2D array of transmon qubits can be used to enable a surface code information architecture. We will be able to drop below the error thresholds required. But there are places where it may be worth it to invest in parallel efforts. And we name those parallel efforts renegade efforts. And for example, one renegade effort we are thinking seriously about, actually we already fund external groups to look into this, would it make sense to build a more protected qubit? Or is this an unobtainium that is still out of reach? But it feels to us, this community that has been thinking about 0-pi qubits or qubits based on GKP states, this may be ready for prime time. And such qubits, of course, could give us more elbow room in terms of error budgets. And of course, the less code distance you need, also your cycle times will come down. So it's definitely something we're looking very serious to possibly have such an effort in-house. But we also rely on the community to look into such alternatives. Another area is asking the question, is quantum error correction beyond the surface code possible? And depending whom you ask, if you go to our own surface code expert, Austin Fowler, he will tell you, no, forget it. If you have a 2D lattice of qubits, then pretty much you are confined to surface codes. Anything you do will look like surface code. And I haven't heard this directly, but it was conveyed to me that John Preskill once said, many people have tried to do something beyond the surface codes, they have failed. So maybe we're stuck with this, but we are not ready to give up yet. And we are definitely interested in efforts to look at more self-correcting codes that could lead to more autonomous forms of error correction. And then the last big worry I should issue is there's still a scarcity of algorithms. So what would we do with this concrete machine? What would we do with a 1 million qubit machine? So this is a little bit more concrete question than just saying, oh, there's a scaling advantage. No, for the cycle times we have, for the remaining error rates that will be there, what are attractive, commercially relevant, valuable, or scientifically interesting algorithms to run? And there definitely we rely on the community to hopefully create many interesting ideas in these directions. And then with that, I wanted to thank you all for dialing in. I know this is a little bit, we all know long video conferences are a challenge, but we try to make it as fun as possible. And I really hope you're going to enjoy the Quantum Summer Symposium.